Yes. Alrighty. Hey guys. We're covering diffusion today. I'm going to preface this very briefly before we actually get into the content of this. This is going to be the most complicated thing that we've covered so far, and it's not even close. To put it bluntly, this is probably the biggest quantum leap we've done in terms of complexity the entire time. For diffusion to work, you need to understand elements of how transformers work, which we're going to be glossing over completely because not worth the time, as well as probably a little bit of physical sciences and probability. It's very, very complicated, and I won't be able to do the topic justice in anywhere near an hour. So we're just going to go through it and figure it out as we go along. So let's get going. All right, quickly. Diffusion is broadly a latent variable model. Basically what this means is that information related from the training data is put into hidden variables. It's put into a latent space. You'll hear about this a lot when you look at diffusion models. It's a lot of the controversy legally associated with them, whether or not information could be considered stolen or copied as a copyright violation by being stored in latent space, even though you won't be able to see it and it's effectively impossible to find. This is potentially where controversy is because the information is hidden and completely inaccessible. So information in diffusion models is stored in these hidden variables in this latent space. The process for forward diffusion and generally also backward diffusion is a Markov process, which I'll cover very briefly in a moment. But until we get there, just think of it as it's an iterative process that I'll go into a bit of detail in a sec. And the forward process literally diffuses information in training images, which again, I'll get to in a moment. So briefly, Markov chains, because this is super important generally, and I'm honestly shocked we haven't gotten to it at all so far. The probability of the current state depends solely on the previous state. That is the entirety of a Markov process. More or less, you don't need to store any of the information that got you to the current state where you are now. If we have we'll cover this in a second. If we have a tree and we have multiple options, what you're going to do is basically just pick the best option and then ignore everything that came before that option. So you're going to take a step down the tree and then repeat that process. It's more or less an approximation of the best estimate process of doing this. There are problems with it that we'll cover in a second, but it has some very major advantages, and it's used basically everywhere when you need to compute probability quickly. The main advantage is the fact that it is memoryless. You don't need to have a huge amount of storage to store like tens of thousands, if not millions or billions of probability states. And you don't need to do a crap ton of probabilistic computations and floating point errors. Really, really useful, used everywhere. But the main issue with this is, of course, that it is memoryless. You don't remember the previous states, and we'll see why there's a problem on the next slide. So as a quick example, just very simply, we're going to pick the option that's the most likely. So for the first node, if we're at C right now, where are we going to go? Are we going to go to 0.8 or are we going to go to 0.2? 0.8, right. So we take a step to 0.8. From here, are we going to go to 0.01 or to 0.1? 0.1, right, very simple. And that gives us a final rough probability of 8%. So what's the problem with our assumption? The problem with the Markov process, very simply, is that we aren't considering later steps. We see here that this is lower, so we're going to outright ignore it, and we're never going to explore that option. It's a very, very simplifying assumption, where in this case, we would have had significantly better outcomes by more than 50% in the best case. We're left with something that's significantly worse. So a Markov process is a very, very useful simplifying assumption, and it's used for a lot of this type of process, but it has a lot of major drawbacks. It's used in a lot of places as well, aside from diffusion. It's used in, I think, transformer models, a lot of large language stuff, just in terms of predictions. LSTMs, I think, use them as well. Very, very useful. Any questions so far? Or rather, how are we feeling about this? Thumbs up, middle down. Cool beans. All right. So the process of forward diffusion. There's two types of diffusion. Forward diffusion literally means, similar to the physical process, information is going to get distributed throughout the image as we have it. So we start at some state, like here, we have this spiral. And then as we add more time steps, it's going to get more spread out and diffuse. It's a similar thing to like gases dissipating into areas of high pressure to low pressure until there's equilibrium. So that's basically the process of diffusion. So forward diffusion, simply, is adding Gaussian noise in a Markov process. You're going to go every single step and add a Gaussian blur, or you're going to add some sort of noise to every single step as you go further down the chain. You do this for 100 iterations, 1,000 iterations, it doesn't really matter. You're going to end up with a crap ton of noise. The diffusion model, the goal of the diffusion model is to reverse this. So what we're going to be doing in theory, by doing diffusion, is we're going to be taking this noisy image and we're going to be converting it into a usable image space. So it's learning how to iteratively remove noise from an image to create new images or recreate the original data in some way. So this can be used as a partial replacement if an image is blurred or is damaged. It can be used to generate new images as seen with like DALL-E or Stable Diffusion or Midjourney. It doesn't really matter. But this is the main use case for it. You're basically undoing the physical process of noise. Yeah. So noise, if we go back, click a slide, you can see basically this is just, you're losing information. So if you look at a very grainy image, for example, that's very noisy. Like TV static is a very, very good and easy example of noise. Like you're losing a lot of information and there isn't a pattern in the thing. It's not crisp, there's no defined edges. Yeah. Yes, exactly. Diffusion, think of it as entropy. It's the physical process of diffusion. Like if you did chemistry, it's just stuff in high concentration moves to areas of low concentration until it's roughly equilibrium. And with infinite time, that's what the process would also do. Okay, so that's the basis of the process. The actual model kind of sucks though in terms of let's covering it. So this is basically where we're going to go off the rails, and I'm really sorry about this. How DALL-E 2 probably generates images, and I say probably because there's intricacies to each one, to each version of the diffusion model, but every single one, as far as I'm aware, uses this rough model shape. So the UNet, this is the basis for diffusion. The original paper, which I referenced early on, that was the actual image of the forward diffusion, uses this general shape. It's a UNet because it, I don't know if you guys can see it, it looks like a U. Wow, that's so quirky. And more or less, the original purpose of this was for semantic parsing. So what that means is you're going to extract a certain area of the image and overlay it on top. Basically here, we can see that there's one dimension here, and the output image here has two layers. So you're able to extract a specific area from the image, keep that. It's not what it's used for now or in diffusion models, but this is the original UNet, as in the original paper. So there are multiple steps for the UNet. The first step is a downsample step, where you basically reduce the size. We'll talk about this more in a second. The bottleneck, which is a small area. This is effectively where the encoding happens. This is the latent space, as we refer to it in a diffusion model, and then the upsampling. And the reason that we use a UNet is because we're able to concatenate the image from downsample into upsample for better predictions. This is also used in locally within the layers in a similar way. It's called residual connections and skip residual network. So similar to ResNet, as I think published in 2015, you skip layers of the network and pass information from earlier layers further on. So it prevents loss of gradient and it keeps information. And I'll talk a bit more about that in a minute, because that is essential to making these models work. All right, let's keep going. Don't you mind pressing buttons? Thanks, Chief. All right, downsampling. Downsampling is pretty simple. Basically, what we're going to be doing is we're starting with a convolution here. We start with our original image. We apply a 2x2 convolutional window. Do another one. This is just to encode the images. Get some. I think it's max convolution. 3x3 window of convolution with a ReLU activation. And then you downstep it. So you do a max pool layer. Max pooling, I think we've covered this briefly when we did convolutional neural networks. You take the maximum value in a window, in this case 2x2, and you set that as the new value of the downsampled image. That's it. And you do that until you get down to some size. I think in the original paper, they did 32x32 for their latent space. And you store that information there. This is making sense so far. This is a lot of information. Yeah. No, downsampling is you're shrinking the image. More or less what you do with the downsample is just represented as a smaller space. So you're teaching the image how to represent. You also do this with the noised image, but we'll get to that in a bit. You do this basically so the model gets a latent representation of what the images should look like for a given size. So given a specific time step of noise, which we can step to regardless because it's Gaussian. So sorry, this is super high level. But basically, because we're adding Gaussian noise, you're able to specify how much noise you're adding. You can literally step from no noise to 1,000 iterations of noise in one step because it's mathematical. It's not like it's a random addition of noise. So what that means is what we're going to be doing is getting the model to represent a collection of these values or some amount of these values latently. So it's going to learn what that looks like and store it in the through downsampling. It's going to be able to compress that and keep it as a latent image, more or less. Again, very, very oversimplified. this model is a pain in the ass to cover. Next one. All right, the bottleneck. Similar thing. Here we're just going to be referencing autoencoding type of crap. We're going to be storing information latently. And what the end result of this is, more or less, is we're going to get a more associative layer here. A lot of these end up using self-attention, which is a thing that's adapted from transformers, more or less, where you pass in information and it gets related to itself in a special way, and then gets stored. It's real messed up, man. I'm so sorry, guys. Yeah.
The downsample or bottleneck uses self-attention?
Both. It's pretty much we'll go over like actual code for this in a minute, just so we're clear. But this is I'm fairly certain the self-attention and also linear attention, same as like a spatial transformer. They're used primarily in the bottleneck. They're also used a few spaces in the downsample. I'd have to remember, but this is a crazy complicated model, so forgive me if I make mistakes.
And also, you said that it ends with a more associative layer, so it's just like
it's I think just fully connected at the bottom. This might be just from the original paper, but I might be misremembering. Yeah, sorry guys, huge amount of information in this. It's hard to cover. Bottleneck is basically just fully connected feed forward for simplicity here. Upsample. All right, upsampling, more or less what we end up doing is we feed information from the original layers of downsampling forward. So we are going to be concatenating just straight up as a skipped connection here. The values that we have here, we store them, and then we pass it along into here and concatenate it. So as you can see, the values here get wider and then narrowed again. We just do convolution basically as a way of upscaling it. So we get a mask of the original image. We store the information from earlier on the same map and do more convolutions basically to keep storing that information. And the reason that we pass it forward every single down and upsample step is because we want to get an accurate prediction of what things need to look like. Again, this is the original unit. This varies slightly when we're going for a more updated version. All right. This is really important. The other ones didn't have words, but this is really, really important to mention. Residual networks and skip connections. The reason that this stuff works is because of residual networks and skip connections. More or less, the residual network is, as published in, I think, 2015, again, I mentioned this, you pass information forward through layers. It allows you to make really, really big neural networks, like on the order of hundreds of layers with like tens of millions of parameters, and pass information from early layers into later layers. So you're going to be missing a lot of the gradient that gets messed up as you go through. It prevents a lot of shrinking gradients. It prevents a lot of exploding gradients if you're doing convolution stuff. And it allows the model to be significantly more precise, just because we're allowing the information to pass through without being altered through convolution or through just a neural network where it's then activated and changed in some way. All right, how are we feeling so far? Yeah.
This, like you have, what do you mean by allows the model to pass through without altering it?
Great. Go back a slide real quick, actually. So basically, do you see the copy and crop here as it's passed forward? That's basically what a skip connection is in this case. This is a very gross oversimplification. It's more advanced later. From the original paper, they didn't really have residual blocks or self-attention yet. This is early still. And as far as diffusion goes, this is a very, very basic version of how this would work. But more or less, the idea is for residual networks, you end up passing information from earlier layers forward. And this is more or less what you would do there. We're just passing information from earlier in the down sample into the later parts of the up sample, just so we can get a closer one-to-one match. 2 slides. Great. Yeah. So the purpose of the bottleneck is basically, it's a representation in latent space. So it's getting the image to it's getting the unit to represent the images in a lower order amount of space, more dense in information. It's basically just an autoencoder. Again, the unit is a really fancy way of messing with information in a way that it can be stored smaller. And the point of this, as in the original paper, is to get very specific predictions. Again, the UNet, as originally published in 2015, was for semantic parsing of images. So let's say I had like a really easy way to describe this would be like an image of a car on a showroom floor. If you want to isolate the car, you could pass it through the UNet and be able to highlight exactly where this is, which is why there's 2 layers of output in the output, and in the original image, there's 1. So you'd be able to, in theory, be able to select a specific area, pass that through, and get that as an additional layer on top. This functionality, I think, was mostly dropped later, except for the fact that you still keep an additional convolutional layer at the end to drop extra layers. So as we can see here, there's 64 layers at the end of the upsample. So we want to drop those down because our original image isn't going to have 64 channels of color. It's going to have probably 3. So we get rid of a lot of those just by doing a simple convolution with like a size of 1. So basically every pixel is recorded and just passed through, and we reduce the number of channels. Does this make sense so far? Yeah, I'm sorry. This is a crap ton of information, guys. There's a reason I didn't really want to cover this, and it's because diffusion as a model is super, super complicated. All right, so quickly, ethical concerns. You guys have probably all read the news at least once or twice and seen the amount of artists and people online generally who don't really like diffusion models because of the fact that it can steal people's artistic style, and pretty easily. If your information is given to this type of model, like sufficiently, you're able to more or less replicate someone's individual style just by getting their collected work and being like, oh, they do this thing a lot, and boom, here's the pattern. And that's what this machine is designed to do. It's meant to emulate these patterns and store them very, very efficiently, which is why it's very useful for image generation. But obviously this causes a huge amount of issues because you're going to be effectively violating the artist's copyright, not really giving them any of the money that they're going to be getting from art made in their own style. It's kind of messed up, simply. So right now, actually, I don't know if you guys have heard of this because I didn't until I started looking. This is a tool called Glaze that was released by the University of Chicago that more or less data poisons. So if, for example, an artist wants to post their information online or their art online, for example, what they can do is pass their art into Glaze. It puts a target style as noise on top of the image, and then if you try and replicate it, you get a whole bunch of crap back. So like you can see here. If you apply no noise, this is like the replicated images from an artist's specific style. And as you go further along, it ends up just being Picasso and abstract art. So you're able to effectively shield all of your images, and it's not able to be replicated as easily in terms of like copying the style, which is really, really cool. It allows artists to keep their own art in a way that is more or less unchanged. The main caveat is that in order to apply this pattern of noise on top, it does visually edit the image. It's really hard to see at this scale, mostly because this projector isn't the biggest, but there is a bit of noise put on top of the cloaked artwork, more or less because of how this works. It isolates an artist's style. So let's say you're putting something out in like a style similar to Picasso, and you want to keep it relatively uncopied by any sort of malicious agent. What you can do is put a cubism pattern on top of it. So take a cubist style pattern, paste that on top of your work, and what'll end up getting spat out is a cubist representation of something. It doesn't even look necessarily like your own work, and it is in no way in the same style. And it's really cool. It actually works. If you look this up, there's a whole bunch of different articles already written. There's a whole bunch of artists who vouch for it. I'm a really, really big fan because it means people aren't getting screwed out of getting recognition for their work or getting their art stolen. So it's pretty cool. And I'm really, really happy to see this stuff. So yeah, this is basically the state of the art in terms of style theft prevention. The paper is also pretty neat. I don't think I linked it in this, which is my bad, but I'll send it in the Discord in case anyone's interested. Pretty simple read. It's a decent bit of fun. And it's pretty cool. Oh, and it's still being updated as well. Like as of 2 days ago, they uploaded a GPU version for Windows. So if you know any artists who want to post their stuff online but don't want their style stolen, recommend them this tool. You just download it. It's open source on their website. You can just look up Glaze. Like literally just the title of this slide, Glaze Protecting Artists from Style Mimicry is pulled from their page. It'll link to their page from to the project page from UChicago. It's really cool. I'm a really, really big fan of this stuff. And it's really nice to see that there's tools coming out to actually keep artists protected in some way. Right. So here's the thing. The really ugly part of this is about to start. And I know it's been kind of hard already, but we're going to quickly open this up. This is a collab notebook that I, for some reason, didn't link. Sorry, one sec. So if you open this up, we'll be able to... Yes, thank you. Just send a link to the Discord. It's a collab notebook that has a diffusion model in it. This model is really complicated, and it's actually significantly more advanced than the early diffusion model as detailed in the UNet. So in that original paper, they demonstrate the possibility that UNets have to like interpolate images. What they did is they took like a picture of some tree bark, filled the middle with noise, and then asked it to interpolate it, and it managed to fill it in a very convincing way. It was like 100 pixels by 100 pixels, but you get the idea. This model is significantly more complicated. It uses residual layers. It uses a lot of inspiration from modern transformers. It's a real beast. And there's probably around 1,500 lines of code in this, which is part of the reason why we're not going to actually be coding this ourselves. So let's get started, shall we, guys? It's real fun. If you want to read through this, they detail probably a lot better than I could a lot of the process of how diffusion works. It's really, really well done. I read through this myself. The neural network, as they detail it here, they define the up and down sampling operations. The residual here, more or less, is just the skip connection. So just feeding the information from earlier layers forward on. It allows you to keep the information, I don't even know how I would put it, locked, I guess, is a pretty good way of saying it. Yeah, and then positional embeddings we don't need to worry about. This is to do with, again, modern transformer stuff from 2017. I don't know how many of you guys have read Attention is All You Need. That's that original paper from 2017. The transformers are everywhere. I hate them. But yeah, so this is sinusoidal positional embedding, which is something taken from those papers. You basically pass in stuff about your data, specifically the batch size and that, and it gives you back the dimension of a whole bunch of stuff to do with the noise. Pain in the ass. So next, there's a residual and convext block. This block is pretty simple. It's just basically convolution and normalization. This is very, very similar to the original step in the UNet. It's convolution, normalization, and silu, which I can actually draw real quick for you. More or less what it is just ReLU, which is the really simple nonlinearity, which we've done millions of times. And the sigmoid function. So silu with like just hold this over here. Silu is kind of just like that. I mean, that's kind of wrong, but more or less, it's just kind of a dip here before zero, and then it's ReLU, more or less. The end nature is ReLU. It adds nonlinearity before there, so it allows you to have inhibitory values, basically preventing any remaining chance of vanishing gradient that you still have with ReLU. Really, really nice. Used literally everywhere, especially in transformers because they hate us. But yeah, it's a very powerful activation function. Question so far, because that's probably the most digestible part of what I've been saying for the past 30 minutes. Yeah. Yeah. So the purpose of the forward step here is basically just to apply this part of the layer. This is just an alias for positional embeddings that we're going to be using later. The forward just means we're applying this layer. I don't think we've done a lot with PyTorch, which makes this a little difficult, but more or less what we're doing is we're taking the amount of dimensions that we have, dividing it by 2, integer dividing it by 2, floor division, excuse me, passing it forward, doing exponential modification in some way, doing I think just multiplication. Yeah, basically. So then if we go to like the ResNet here, where is it? Just here. How about this? So I do that. So if we do this real quick. This is called, I think just in the ResNet block. I could be misremembering, but it's just a forward step that's really important for getting the information actually sorted. Again, my expertise is not transformers. I have been doing research in the past 2 months specifically, not for this talk. That would be really embarrassing if I was going to be researching for something that I'd be talking for an hour. No, I'm doing actual research to do with the diffusion models. This is not my expertise. My expertise is figuring out specifically how these types of models run. And this is not it for now. I only found this a few days ago. So within a week, I'll probably be able to explain it a bit better. But yeah, basically the ResNet block here is it's a residual connection, or sorry, I don't think it's a residual connection. Residual connection is something else, but used basically in the UNet itself. So what we're going to be doing in the UNet, it's going to explain this in a bit as well. You're going to be interleaving attention and ResNet layers. So just basically interleaving blocks and attention, and it's going to be interpolating more information. It's a huge step. I really don't know why we did this. It's kind of hard, but all right. Also, feel free to ask questions because this stuff is great. It's super awesome. So yeah, here's attention. Again, straight from transformers. They apply both attention and linear attention. They also do just straight spatial transformer stuff. Where we end up applying like convolution again. I think we briefly touched on how this works, but I don't remember. And then just linear attention, which is just more or less more complicated. Doesn't particularly matter. Group normalization, just to normalize the values that get fed into the transformer. It's used to basically minimize the amount of noise that's there. And here's the UNet. All right, we can actually talk about this one a little bit. So similar to the actual paper from 2015, the order is as follows. You first add a convolutional layer. So this is just to, I think, apply some positional embeddings. I could be misremembering, but you just basically apply convolution over the original image, get information applied in that way, and then you continue till the next steps. You do downsampling. Each downsampling stage is 2 ResNets, a group normalization, attention, a residual connection. So you feed the information forward from earlier, and then you downsample. And the specific part that is to do with the downsampling is, let's see, it is right here. This is the downsample. So we're going to be adding first the block, another block, residual, the residual connection, and then the downsample. Pain. And then, yeah, the bottleneck here is more residual blocks, a residual connection, and then more blocks. You apply attention as you apply each of these specifically so we can keep more information. Again, can't explain it. I'm not a transformer guy. That's Michael Bay. Terrible. So, and then here's the upsample. It's basically just the reverse process. The nice thing about the UNet itself is because of its shape, the upsample process is literally the opposite of the downsample process. So every step that you do in downsample, you basically do in reverse for the upsample. The only difference is that you also concatenate images from the downsample as well. So you pass a lot of information through. So before you, so before you like actually edit the thing. Oh, that's weird. They do it backwards here, but it shouldn't really matter. Yeah. Apply what? Sorry. Oh, on each downsample step, like here. So what you do is you first apply the block, which is which we talked about earlier. It's just more or less the residual. You apply another block, and you apply. Sorry, not a residual. You apply a block. So ResNet, another ResNet block, a residual connection. So pass information forward, or retrieve it from earlier, I guess, and then you downsample, which just compress, right? Yeah. More questions. Please ask them. Yeah.
Don't think we talked about what attention means.
Yeah. Do you have a good explanation for me? Because
yeah.
Be my guest.
Essentially it's looking around at the nearby data and trying to figure out what of it is most important. So it's looking at the nearby data and basically saying, this is the stuff I should be using to try and get my output. Yeah.
So in that sense, basically why we apply attention is just to keep more information. We're able to amplify specific things about the noise that are important to reference later on, pass them through, store it, more compressed, decompress it. how this works is kind of magical, I'm gonna be honest. And part of the reason that it takes so long and it is such a complicated process is because you're trying to undo a process that naturally adds noise. So we're basically trying to calculate the opposite of a Gaussian blur, which is insanely difficult. In theory, you know the exact model just by applying it, but the computer doesn't. And if you wanted to generate specific types of images, you needed to do it generally as well. So if you have a general pattern of noise and you wanted to generate an image of a dog or an image of a cat, it needs to know that different conversion as well. So this doesn't, I think, have, you can't actually specify exactly what you want it to convert. That's a whole other process that I actually don't understand and have been trying to figure out for about a month. But it's basically just getting it to learn different patterns of noise in some way. So doing iterative training, getting all that. Realistically, this could take, I don't remember exactly how, they don't state how long their model takes to train or on exactly what hardware, but this could take anywhere from like 10 to 100 hours to get something that looks decent for, small pixel sizes, depending on how big your data is. Like speaking personally, I've been running tests on my own hardware for generating images about 32 pixels big. That took around 14 hours to get something that looked convincing. And then I let it run for another 10. So yeah, and then for 64 pixels by 64 pixels, I ran it for about 40 hours and it never converged. So this process takes a really long time, even if you have really good code, and I don't. So it's a very difficult process, and it's a very difficult process to explain as a result. For diffusion process, we've talked about a little bit. I could talk about specifically why they apply cosine noise, but more or less as a simplification. If you apply noise linearly or in any other method, what ends up happening is you apply noise towards the end too quickly. So you transition from an image that is recognizable to an image that is completely noise almost in about 5 steps, if you're adding like on small enough increments. And it's impossible to really train that. So they found that just through brute force experimentation, cosine is a very good approximation for a pattern to do that with. So it just adds noise a bit slower. So it's the cosine beta schedule. There's also just linear, which is slightly worse. Quadratic, worse. And sigmoid, which was honestly my first thought, because sigmoid makes a lot of sense, but somehow cosine's better. And so then here, this is just them applying the noise as a sample and then visualizing it. I'd have to run because for some reason this isn't showing. That's annoying. Oh, that's weird. It didn't save it. That sucks. So I don't know if you guys can see this on your end specifically. But when they sample it here below the cell that creates a GIF, this is probably right near the end before follow-up reads. There's a process that basically is a GIF of iteratively adding the noise. So if you like, it for some reason isn't showing up here, but basically it starts out being completely noisy in a 28 by 28 pixel area. And at the end is basically a 28 pixel by 28 pixel of a long sleeve t-shirt, which is really impressive. They were able to just iteratively show you the process of diffusion. It starts out with completely noise and slowly advances to a shirt. And I'm upset that you can't actually see that process because it's pretty interesting. For some reason that's not showing. Actually, let me see this. Maybe we'll be able to do something. Reload the page. Oh, gosh. Ooh, we loaded? Nope. All right, hold on, we got this. It's easy peasy. All right, here we go. So as you can see, it like kind of iteratively removes the noise. And then all of a sudden, wow, it's a white t-shirt. Look at that. That's so cool. And that's basically the process of diffusion. What they used for their data set is the MNIST fashion data set, which I think is a part of, well, I think this is just a part of PyTorch, if I remember correctly. Point is, it's a really small data set with a whole bunch of shirts and stuff. And they let it generate a t-shirt after training for a crap ton of time. Yeah.
Well, as in number of images or image size?
Both, I think. The MNIST set itself, I'm pretty sure is like, I'd have to say the actual MNIST data set is 32 pixels by 32 pixels. I don't know the amount of the amount of images in the data set, but the fashion data set I think is only a few thousand images. But these are pretty small. The patterns are pretty much the same. There isn't a lot of information they need either. They're doing like I think just one channel of color. which makes it a lot simpler. You don't need to store colors. Yeah.
And this is different from generative models?
This is a generative model. Just in the sense that instead of like a GAN, which competes against, which is just effectively a zero-sum game between a discriminator and a generator function, this is just going to be generating images from noise. So we're going to be starting out with a completely blank slate and asking it to make us something like this, right? So this.
You put it together then?
So that's, I actually talked with someone about this earlier today, specifically making a loss function that compares that, because a lot of so an issue that I noticed in my testing personally, the loss function that you end up applying either is pretty effective early on, because what the loss actually ends up doing in this type of function is it models the change in the loss itself. It doesn't it models the change in the noise. It doesn't model the success of the image. So what I was thinking is, why not just define some sort of loss function that allows you to straight up compare the image that you generate to the images in the original data set and get some sort of prediction that way. But I'm pretty sure it doesn't really add much. Yeah.
And also the incredibly time intensive.
Probably.
Creating each image itself takes an absurd amount of time, and then if you wanted to create the image and then compare that to something multiple times, it would just be.
So actually, sampling doesn't take that long. It's because there's so many parameters, and the process of descending the gradient is very, very expensive. This takes a while, primarily just because there's a lot of stuff you need to calculate and a lot of stuff you need to update every single step. Like you can see in one part of their code, they end up saving a sample every 1,000 time steps or so, which I think is specifically because they have a lot of really small batches, not because of anything else really. But you end up getting something that's more or less just, I don't even know. It takes a while, to put it simply. So yeah, it's an interesting thing. I've thought about it literally today, if it would be possible to just like increase the effectivity of the model by adding a loss function that doesn't discriminate based off of the comparing noise to an expected noise pattern, but actually generating stuff and comparing it to the data set itself. Yeah. Yes, of course. Loss function. I'm so sorry. I should have explained that a bit better. A loss function more or less assume that we have some sort of function, right? Our function in this case is going to be defined as Our function in this case is going to be defined as some sort of landscape. So we're going to be looking to approximate a function as well as possible. So it could be anything. It could be classifying one type of fish from another. It could be grouping in multiple types of clothing together, t-shirts to long sleeve t-shirts to blouses to tank tops, whatever, right? The loss function more or less is a way for you to model how far off you are. So that if you say, for example, that you assign a score to each probabilistic comparison of like, is it this type of fish or this type of fish? However confident that is, that influences the score that gets applied to the loss. So you can do a whole bunch of computations and it gives you some sort of number. Let's call it 13 in this case. The goal of your optimizer in that case is basically to make this number go smaller. And that's by the process of gradient descent. If we have this is a very big approximation, but if we have like a 3D loss landscape, which is basically just hills and valleys, the loss function models this landscape. So if we were to get the loss function at every single point for every single possible generation, this is what it would look like, some sort of space that we can traverse. The optimizer's goal then is to basically descend this landscape to the lowest possible point, some very good approximation. Does that make sense? Perfect.
Approximating, you're just comparing it what you made to what the actual answer.
Yes, but in this case, it's a bit more complicated because the loss function in this case is going to be comparing the pattern of generated noise to the pattern that the model generates in some way. So what you're going to be doing is basically comparing how well can the model simulate this applying noise, this application of noise or whatever. And so as a result, if we scroll a bit further down, it's right by the bottom. Nothing particularly changes. So if we go to like here, like this is the loss. You can see that it starts as like a fraction of 1, and then it's basically the same from epoch 5 to epoch like whatever, or whenever they index it. It doesn't particularly matter, right? But it doesn't particularly change, and that's because nothing is changing in the model. It's just a question of modeled noise. Yeah, so this is a very, very complicated thing to talk about in an hour, much less when we haven't covered a lot of the stuff that you need to know to get into it. So my suggestion for you guys, if this is interesting after my very whirlwind explanation, read through this notebook. They have a very detailed mathematical and just English explanation of how their model is put together. They also link all the papers that you need to understand this stuff, which is really huge. And then if you want, run it. Spend the time. I don't know how long this will take. My estimation would probably be on the order of a few hours running this in a collab notebook and see what it spits out, because it'll probably be interesting. But as you can see, Cohn's been running this for 3 minutes. We have 1 index here. It's a slow process. So I would suggest running it, but it's expensive. Yeah. Yes. Yeah. Every model tends to have its own loss function. It depends on what task you're doing. Sometimes it's better to represent with just average error, sometimes something else, sometimes mean square error. There's a whole bunch of functions for literally every conceivable purpose. It just depends, really. But yeah, every single AI function has some sort of evaluation metric or loss function. It's based off output. Like if you're doing a search task, for example, it could be like it could be distance from the goal or just like some sort of target. It could be whatever. If you're doing like a classification task, it's going to be accuracy or like the error in some way. If you're doing a generation task, it's going to be some other comparison. It again totally depends on the task, and it varies for each different thing. It's all contextual. No, not necessarily. You could just define like some sort of distance evaluation metric. You could do a whole bunch of different stuff. It depends, really, is the answer always. There's unfortunately, very little cleanly cut answer in any of this. And it's a lot of try it, figure it out, or see what other people have done, because that tends to be pretty good. All right. Any other questions? Yeah.
At the risk of beating a dead horse a little bit, the loss function that this one uses, you said it compared the noise that it generated.
Yeah.
How is that a measure of its efficacy?
So here we could see how they define it, I think.
Like, wouldn't it be the noise that it like ungenerates or removes?
So yes, this might just be my own code leaking into my brain. Because what we had when we were initially testing stuff is the loss function was evaluation of generated noise, because I think it also models forward diffusion. I might be misremembering, but there isn't a very easy way to compare, or maybe it just might be, oh, this is very difficult. It's hard to navigate this stuff. Let me just see. Can I quickly? That should be an underscore. That's an enter. Wait, seriously? Where's the other one? Anyway, oh, is it maybe hidden? Yeah. Which cell are we in? Which cell are we in? Yeah, that's probably the biggest issue I have with this. Too much stuff. It's really big. Like I said, there's 1,500 lines in this. I'm really struggling to navigate it. It's probably fine. Yeah, this is what they test their application of noise on. It's pretty cool. And then for some reason it did. Oh, there you go. It's like this is their application of noise for like random time steps for like step 0, 50, 100, 150, 199. And you can see it just iteratively adds noise.
That must be feeding like some completely random noise. That's not related to what's generated.
What? Oh, I mean, it's gonna probably seed it correctly. It's randomly noised, right? It's like it's Gaussian, so it's a probability distribution where some things are gonna be noised more often than others, or in a predictable sort of way. And that's really nice because in theory, if you know the noise function, you can undo it per time step. And again, that's what the model's trying to learn how to do, because you want it to be able to generate, in theory, new images or repair old images in a way that adds noise. Or incrementally removes noise. My bad. Yes. Sorry.
And like, I don't know if it's too advanced, but like how do like modern diffusion models like take like a cat image and then diffuse like add noise?
Yeah.
And then undo the noise and make it like a cat with elephant features.
So that's okay. This is something that I'm trying to figure out. Just to preface, my research is to do stuff with these types of models. We're trying to make synthetic data for whatever purposes, right? We need to be able to specify values that we want it to generate specifically. So based off of the training data, given like a CSV of a whole bunch of values or whatever, be able to take that and then we can give it something similar, and it'll give us something we can evaluate to be similar, dissimilar after some amount of training, generally, right? The way that it does that and applies features, I think it's to do with latent representation of the images. It's you're able to apply different noise functions and unnoising functions given different inputs. Like the images that it generates obviously have never existed before, right? That's the whole beauty of doing diffusion like this. You end up getting stuff that you've never seen ever. So what ends up happening is you can like give it a specific image and it feeds out something similar or roughly similar that has, I mean, elephant ears. Stable Diffusion has this. You could actually just go to their GitHub page. I was trying to look at this also today to see how they add stuff. It's real wild.
Stable Diffusion not use like any human like saying, hey, this is a good image and this image makes sense to me according to the model.
Sure. Let's see. I mean, yeah, give it whatever. Seriously? How do you spell banana?
Yes.
That's a good point. That's a good point. All right, generate. Let's see what happens. Oh, this is their hugging face thing. But yeah, you can see it's like 8 seconds to generate the image. The thing that we're trying to do is to do with like 3D diffusion stuff. So an image from the current state of the art took like 12 minutes to generate in browser for me. Oh yeah. It doesn't know what a banana slug is. It knows what snails and bananas are. That's cool. Guess that's a bit too esoteric, but like you can see, there's issues with it. It's not perfect. It's a question of tagging and evaluation in some sort of way. I don't remember exactly how they do this. I've been able to read their papers. I haven't been able to look at their code too much, but I'm sure. Yeah, I think the banana slug is a little too esoteric for it. Truly, we have no known predators. Am I right, guys? Yeah, let's go. Bunch of yellow slugs. And then workshop. Let's see. Oh, you should have said a cornucopia, because then it would have understood. Oh, there we go. It's just tiny bananas. Good stuff. That just looks like a bunch of tiny bananas. Am I wrong? Like, I mean, it's yellow slugs. It's got that much at the very least. Yeah. I mean, again, hard to say. If we said a cornucopia, I think it would have got it. Yeah, cornucopia banana slugs would have been locked in immediately. Yeah, that's why the fall event is called cornucopia. Yeah. But yeah, that's basically diffusion explained poorly in about an hour. Again, if you guys are interested in this, I'm not going to be able to do it justice in any amount of time. This is a really, really complicated thing to just even cover generally. Best thing you can do for yourself is read the papers, experiment running the model. Like the workshop, the notebook that I just gave to you guys has every single paper that is going to make it understandable. They've linked to the original paper on transformers, the original paper on UNets, the Google Brain original diffusion model to generate images. It's all that specific collab. I don't remember. They link themselves at the top, though. I'm sure they have GitHub pages as well. Very smart people, I'm sure. I haven't been able to look at any of their other work. You just scroll to the top, they're linked. Yeah. So yeah, those are the guys. I'm fairly certain they modified. Oh, that's impressive. It just looks like slugs. That's okay. Anyway, that's more or less all the information that I can effectively give to you guys in one meeting. It wasn't a lot either, because this is super deep. But yeah, if you are interested in diffusion stuff, it's very hefty. Start by reading up on the original unit. The paper is like maybe 20 pages. My God. The original paper is like 20 pages. The oh, this is, yeah, make a video. I think it's kind of weird. Oh yeah, Meta did this. Read the original paper on UNet. It's 20 pages, really easy. Oh yeah, 100%. I'm going to link all the papers that you probably need for this. It's also linked in the collab notebook. Every single paper that you need to be able to understand what they have in there is linked. They did a really, really good job. I'm very happy that I was able to find it. They linked the UNet, they linked Google Brains paper, they linked the original Transformer paper from 2017, they linked paper on ResNet, they linked the paper on skip connections, they linked everything that you need to have to understand this model probably better than I can explain in the collab notebook. Super, super useful. But yeah, that is basically all the information today. So in case you guys have any other questions, I'll be up front for a couple minutes, but that'll be it. Thank you guys for coming. And quickly, yeah.
Class goes over this year.
Diffusion,
Or is it just kind of get into the research?
it's diffusion. I'd be really, really pressed to find anyone who wants to be brave enough to teach it. Because the closest you'll probably get, CSE 143 covers transformers at the end, and very, very briefly, because it's super complicated. Very, very, very esoteric stuff. You need to be very in the know, and you need to read a whole bunch of papers to get a decent grasp on it. It's probably a year-long class, Christ.
A CS class that required every single math prereq that the school has to offer.
As well as like, I don't know. This is like incredibly high level. If you want to do this stuff, read papers, watch tutorials, run it on your own hardware or in a cloud thing. That's probably the best thing I can suggest. But yeah, this stuff is hard. This is really, really hard.
To actually understand it is who's the people who put their entire lives to solve this type of thing. So as an undergrad class, I don't know about us, right?
Like, yeah, again, just so we're clear, I've been doing research on diffusion models for 2 months. It's hard to explain, real hard to explain. So yeah, bear that with what you will. It is very possible to understand if you read all the papers. It's just, yeah, that's probably a good place to go with it. Yeah, so diffusion's black magic, and that's more or less our meeting. Thank you guys for coming, and I'll be up front for a couple minutes if you guys have questions, but oh boy, I'll try and answer them.
Thank you.
Yeah, appreciate you guys. And then,
I'm submitting the SILCA application.
Yeah.
For.
I'm sorry,
Guys know what?
you need that in the recording. This is the original thing, or roughly in 2015.
For all.